In the instrument detection settings, we will set the excitation wavelength to 488 nanometers and the emission wavelength to 525 nanometers. We will also set the instrument to read from the bottom of the microplate. We are now ready to perform an initial scan of the plate in order to observe the baseline fluorescence values, evaluate the well-to-well variability, and determine the signal to background. If you remember from day 1 of the protocol, when transducing and plating the cells, we made sure to include a set of control wells with untransduced cells. These wells should have fluorescence values significantly lower than the transduced cells. In the experiment here, you can see the untransduced control in the light blue outer wells of the plate. The transduced wells, indicated by the dark blue inner region of the plate, have fluorescence values roughly 20 times higher than the untransduced wells, indicating high signal to background. Having high signal to background is an important factor in achieving optimal assay performance. Low well-to-well variability is another important factor. We are now ready to run the assay, which will consist of the plate reader performing multiple read steps in kinetic mode, adding an agonist, and observing the caddis sensor responding with a large change in fluorescence intensity. In this experiment, we will be adding the agonist isoproterenol to activate endogenous beta-adrenergic receptors. This, in turn, will lead to activation of adenyl cyclase and the production of cyclic AMP, which binds the caddis sensor. We will be adding the isoproterenol in 50 microliters of DPBS, such that the final concentration in the well is 10 micromolar. Since the plate washing protocol left 150 microliters of DPBS in the well, we will need to prepare the isoproterenol at 40 micromolar to account for the 1:4 dilution. It is also very important to designate a set of control wells to receive vehicle alone to make sure there's no artifact from vehicle addition. Our vehicle control will be DPBS. The plate reader should be programmed to perform a kinetic read. Typically, several baseline reads are required. The program is paused and an agonist is added either manually or with an onboard dispense system. Reading of the plate is then resumed. It's important to make sure that the kinetic settings are compatible with the kinetics of the sensor signal, so as not to miss the sensor response. Here, we will program the plate reader to measure the plate once every minute. As we saw before, the fluorescent signal from the transduced wells is much higher than the control wells in row 1, indicating high signal to background. The signal should be stable as you monitor the baseline fluorescence. A sharp decline in signal may indicate photobleaching, and if so, the instrument settings should be adjusted to reduce the intensity of the excitation light. After several baseline measurements are required, the agonist will be added, as well as the vehicle-only control. It is very important that the dispense be done gently so that the cells are not dislodged from the plate. Here we can see the cells responding to the agonist, indicated by a dramatic increase in the fluorescence of the caddis sensor. The signal takes around 6 minutes to reach saturation, and by that time, the caddis sensor fluorescence has increased by about 250%. Notice that no change in signal is observed in the bottom 3 rows, which is the vehicle-only control condition. Another thing to note is the low well-to-well variability, especially with regard to the percent change in the fluorescence of the sensor. This low well-to-well variability, combined with the robust change in fluorescence, allows the Caddis assay to achieve Z-prime values of 0.9 and above, and makes it possible to generate accurate dose-response curves. This concludes the tutorial. Please refer to montanamolecular.com for more information on products, troubleshooting tips, and frequently asked questions.